Alright, so hello and welcome. Here's another problem to work on. Just give you a moment to make sure everything is working before I begin. So print problem to work on, just give you a moment. Print FooBar alternately, problem 1115. Let's take a look at this. So okay, think everything is working. I'm just wondering if there's anything I don't want to show. I think we're okay. Just give me a moment here. Yeah, I think we're in good shape. Okay, very good. So, there we go. So let me turn this one off, close this one. This was 11:11, and I'm gonna go into 11:15. All right, a little nervous, I don't know. I took us kind of a break earlier, and I just kind of want to get, I want to get 7 more questions done in the next 3 hours, see if I can get that far. All right, so n is between 1 and 1,000. You've got a higher submission rate, higher acceptance rate, but a relatively low submission rate. Not that low, but on the lower side. Suppose you were given the following code: FooBar, I is 0 to n, print foo, where n I assume is probably some member, and bar prints foo a certain number of times, prints bar a certain number of times. Same instance will be passed on 2 different threads. Thread A will call foo, while thread B will call bar. Modify the given program to output FooBar n times. Excuse me, so it seems to be multi-threaded. Interesting. 2 threads being fired asynchronously. One of them calls foo while the other calls bar. FooBar is being output 1 time. Output 2 times FooBar. So I guess this is a practice with multi-threading. Forced multi-threading practice. I mean, not the worst thing. Do not change or remove this line. I don't really understand. How many upvotes? It's got a lot of upvotes. Yeah. I don't really know what's going on here, what they want me to do. I don't get it. The first impression, I don't get it. Okay, so case 2, foo bar bar. Case 3, foo a bunch of times, bar a bunch of times. Okay, runs them on different threads. I mean, I can add a lock, I suppose. A mutex. Lock guard. I don't remember. I don't even really know, quite frankly. I don't use these things so infrequently. LockGuard is a mutex wrapper that provides a convenient RAII style mechanism for owning a mutex for the duration of a scope lock. When a lock guard object is created, it attempts to take ownership of the mutex that is given. When control leaves the scope in which the lock guard object was created, the lock guard is destructed, the mutex is released. Okay, so basically, standard mutex lock GI mutex protects GI. Mutex. Thread 1, thread 2, mutex, G pages, mutex. Result, fake content, lock guard, mutex guard. G pages URL, result, save page. Thread 1, thread 2, FooBar. simulate a long page fetch string fake content. So sleep for 2 seconds. Create a lock guard that'll guard this mutex, and then try to write. So I think when you obtain the mutex class synchronization, a primitive that can be used to protect shared data from being simultaneously accessed by multiple threads. Mutex offers exclusive non-recursive ownership semantics. Calling thread owns a mutex from the time that it successfully calls either lock or try-lock until it calls unlock. When a thread owns a mutex, all of the threads will block for calls to lock or receive a false return value. Try-lock if they attempt to claim ownership of the mutex. Calling the thread must own the mutex prior to calling lock or try-lock. Behavior of a program is undefined if mutex is destroyed while still owned by any threads, or if a thread terminates while owning a mutex. Mutex class satisfies all requirements of mutex and standard layout type. Mutex is neither copyable nor removable. I think I could just do something like the following. Standard mutex mute. I don't really know what to. Yeah. And then I can just do put this in a scope. Don't change or remove the line. Well, I could indent it, right? Standard lock guard, which I think is just standard mutex. Not sure why it's templated, but okay. Guard, mute. I think it's or lock. Could also lock. And then the same thing over here. I wonder, so this is not quite right? This has to complete before this can execute, before really the next line can execute, nor this one can execute. The problem is, I mean, there are different ways I can do this. I don't necessarily need a mutex for this. There's another kind of lock, which is has a semaphore. That's the one I'm looking for. or allows more than one access the same resource. Binary semaphore? I don't really understand what semaphores do. So more than one thread can access a resource with a semaphore at the same time, which is a little bit weird, but okay. I think what I want is I don't want to allow bar to be printed until foo is printed. And I don't want to allow the next foo to be printed until bar is printed. Gotta go foo, then bar, foo, then bar, foo, then bar. Foo, then bar, then foo, then bar, then foo, then bar, right? And this idea of trying to use a lock guard doesn't quite achieve what I was hoping for. I could have a bar counter and a foo counter and wait until foo is incremented, but I kind of want things to be a little bit more, I don't know, do things a little bit better than that. I mean, I could just have a busy loop for the thread, just count how many foos have been printed. If more foos have been printed, then, or yeah, if there aren't enough bars have been printed, then I wait here. Same thing, if there aren't enough foos that have been printed, wait here. I mean, that's one way of doing it. It's not really great to do it that way. But here's one idea, right? Be like the following. Foos and bars, right? We would say if bars is less than foos. Yeah. And this is another busy loop. While the excuse me. While foo is being printed, I need to wait for the next bar. So we'd say, well, I would say, well, they're not equal. We'll do it that way. I don't know. Print foo. How does this work? We're waiting for bar to print, and then foo and bar will be equal to each other. So while foos is greater than bars, while bars is less than foos, we're waiting for bars to finish, and then they'll be equal, and then we can print foo. And here we're waiting for foos to finish, so while foo bars is equal to foos, we keep waiting, and then once foo is printed, then bar can be printed next. Something like this. Something like this. I just time out. Okay. Hi, Will. Hey, what's up, Malik? Hello. Hello, hello, hello. Hope you're doing well. Welcome. I'm kind of stuck on this question here. Kind of stuck in some way. Malik? Hello. Not sure how to say your name. I'm assuming it's Malik. I'm wondering which of these is getting stuck on. Stuck 1, stuck 2. In theory, something like this could work. In practice, I'm not sure. Maybe I'm missing something important. So yeah, I have to admit, I don't have a lot of experience with concurrency. I know a few things about it, but I'm not like extremely proficient. Oh. It worked. This time it worked. You know, maybe they both locked before. Got some kind of deadlock. That would be interesting. They both ended up in a while loop. I think I should have the two conditions be different from each other. Well, they're not equal, so they can't both be going at the same time. How about that? Like that. I like that. That might be better. Better condition. It's only one while loop can be stuck at a time. Oh, huh? Interesting. So when I inspect it, huh. When I inspect it, it works. When I print some statement out, it works. But when I don't print a statement, it doesn't work. I don't know. So when they're not equal, but they start off as equal, maybe I'm doing something strange here. I'm wondering if this is initializing the way that I think it does. I think this is. Actually, I think when it TLEs, it won't. Oh, it does print it. Yeah, okay. So they're both 0. Foo and bar begin. These are equal, so here this just keeps going. Here they're not equal. They are equal, so this continues. We print foo. Foo should be incremented by 1. Then these are not equal. This one opens. Prints bar. Foo and bar. Foos and bars are then equal again. Then this one opens. Should kind of alternate opening and closing the loops. But some reason it doesn't. I don't know. It's a busy loop, but it's like, I don't know why. I don't know. Doing something that's not. I was hoping maybe I could do a really simple routine would work here. Hoping a very simple routine would work, but apparently not. I was hoping a very simple routine would work here, but TLE 0, 0. Okay. A few things to say about this. I was hoping a very simple routine would work. Let me get rid of these test cases. Let's go for 2. keep it simple. I was hoping a very simple routine would work here and I wouldn't have to think too hard about this, but I think I need to reassess what I'm doing here. This doesn't work. So we get 0, and then the other one gets a 0, and then it just gets deadlocked. And the question is why? Foos and bars should be equal to each other. So once this occurs, I increase. Yeah, they're now no longer equal to each other. Foos and bars, and so this should keep looping infinitely. And then over here, this one should have been waiting for some time. Once this completes, foos should be incremented, and these should be no longer equal. So this should open, which it does. And this gets printed, and then we increment bars. Oh, I think I know what might be happening. Okay, let's try that now. I think I know what might be happening. Okay. I think I got it. Now I can use my lock guard. I think this works now. That could be the problem. Race condition. It's a race condition. Okay. Yes. Didn't even consider that might be the problem. Ready for that? How about that? That could be the problem. That would make sense. That might be why before. Still TLE. No, not the problem. I was thinking maybe that's why, because I was printing something before, it wouldn't just immediately go into you know, I'm not really sure about this actually. Maybe the whole thing has just got to be locked. I don't know. One has to wonder. Oh boy, I don't know. I don't really know why this is causing me is wrong. My thinking before was that, well, maybe maybe I was basically running into a race condition where because I was basically incrementing foos and bars simultaneously. I don't know how it's possible that that could lock, that both these while loops could be. I mean, maybe what happened is that this printed. No, it didn't print. No, both of them, they got deadlocked. I mean, it had to have deadlocked. Somehow it deadlocked. I don't know how can you have two conditions that are different deadlock? How does that happen? How is that possible? How is it possible for this to deadlock if these are both? These are the opposite conditions, right? Oh. Put the lock above. That's bizarre to me. I don't know what to make of that. But this mutex, this lock, should guarantee that. Which actually, maybe this shouldn't be. This shouldn't be with a lock. No, that's wrong. This is wrong. This one obtains the lock, I guess. One of them obtains the lock, and the other one can't. That'll definitely deadlock, because, yeah, I don't know why. I don't know, maybe I don't use a lock at all. That's really confusing. This is so confusing. Why is this happening? I don't understand. I don't know. Yeah, you get to watch me suffer and struggle as I wonder about some of these concurrency primitives that I basically hardly ever use. I like concurrency, but I don't like to use locks at all. I think using lockless concurrency is quite good. Yeah, what is happening? Why would this happen? Why would this happen? As soon as I put a print them though, I get as soon as I print something in these loops though, they no longer have race conditions, or whatever you want to call it. They no longer, like, TLE, no longer lock. What's the word? Deadlock. They no longer deadlock. So we have 0, 0 initially. Foo of I 0 is printed right there. This is while they're not, so they're equal, immediately goes through here, and foo's increments, right? Over here, if 0, 1, they're not equal, this one is just repeatedly looping. Then we'll say bar and foo, so I can recognize where these are being called from. Yeah, what is it doing? How is it getting stuck? Foo of I is 0. So it calls 0, 1 foo bars. And they're not equal, so it keeps looping, right? Busy loop. Then bars 0, 1 is also called. And this should keep, these are not equal, so this should not loop. So bar of I 0. And then print bar and bars plus bars. Okay. And now this loops again. So this one is still going. Bars is not equal to foos, 0, 1. This one becomes 1, 1. Bars is 1, foos is 1. This is now 1 equals 1. And this should keep looping. So this one should lock, but this should unlock. Why is this? Why is this? Why is it just looping indefinitely? Isn't it supposed to? What? Do I need to, like, wait or something? What is going on? What? Go up? When bars is 1 and foos is 1, this should open. What is going on? I think it works if I do this. If I flush the... What is happening? What? Yeah, so there's got to be something going on here that's like... I suspect it might be like an optimization of some sort. Some kind of compiler optimization. No, TLEs, no. It's just 0, 1, 0, 1. This just keeps going forever. No. 0, 1. right? Then bars, bar 0, 1, bar 1. Okay, so it loops for a while the other one prints. Then we have bar of I 0, increment bars. Now they're equal to each other. Bars 1, 1. This is looping infinitely. And then here we have this 1, foo's 1, foo of I 1. So this one moves forward. This one moves forward. And this has got to be some kind of optimization thing. It should. What is going on? This definitely should work logically. Like there's something going. Yeah, okay, of course. Gotta be kidding me. Oh my goodness. Serious. Something bizarre going on here. I don't know. Like, what? It just like locks itself permanently if the condition. What? How does that make any sense? What is going on? Oh my goodness. Okay. Maybe I'll try pointers. That's really strange. Yeah, I don't know. It's so odd. Why? You gotta be kidding me. Why is this happening? How is that? How is this possible? I don't understand. I don't know what's going on here. What is it doing? There's something. I feel like I'm missing something important. I must be. Why would this lock? Why would this deadlock? I mean, these are opposite conditions. How is it possible that they're what? How is it possible that they're both looping infinitely? Oh, this doesn't make any sense. Something's not right. I feel like I should know this. Like, why would this loop? I want to. It's got to be an optimization of some kind, compiler optimization. All right. Deadlocking while loops. I know there's another way of doing this, but it's got to be some kind of compiler optimization or something. Like where. Basically just what if I were to do this, like dereference and get the reference and dereference to force this to see if that even compiles, to force this to try to find compiles. I'm sure there's a more appropriate way to do this, but also, why doesn't this work though? That's absolutely perplexing. It's kind of what I'm focused on at the moment. I feel like I should know why. Oh, now it's working. Okay, of course it is. Oh, you gotta be kidding me. Really? Yeah, it was a compiler optimization. I'm pretty sure that's what it was. Yeah, compiler optimization just wasn't checking the values there. Dude, that's wild. Oh my goodness. Oh man. Gee, no problem now. No, it's no problem. Of course. I mean, how much time did I spend on that? I spent like 20 minutes just staring at this. Like, it should work. It should definitely work. These are literally opposite conditions. How could they deadlock? How is that possible? Compiler optimizations. That's got to be it. It's got to be. It did some kind of compiler optimization and just decided that because there's no update to this variable within the thread, then you could just optimize out the condition check. I'm sure it had to have been that, something like that. Yeah. That's pretty encouraging, these test cases I have here. I'm gonna try a few more because I'm not too sure about this. This is pretty I'm like afraid to submit this here. 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so how's that for some C++ specific use, knowledge here? 13, 14, 15, 16, 17, 18, 19, 20. I don't think it's possible. Like I said, I don't think it's possible for this code to deadlock because there's opposite conditions aside from the compiler optimization. Sometimes it runs a little slower though, huh? All right. Anyway, I'm going to try to run this. I'm afraid to submit it, but I'm gonna go for it. Afraid to. There we go. Okay, we got it. All right. Slow, but we got there. It's like, oh man, of course. Submit it a few more times. All right, I should think about a better solution than this. Just a busy loop. I mean, this is like probably as fast as it goes, right? I don't know. Is there? Oh. A full 966 milliseconds, of course. Of course. Just what happened there? Maybe I should look at the discussion for this one. Let's try again. Oh, that's brutal. Oof. Okay, now it's going a lot slower. What happened? What happened? Why is it so slow now? What is going on? One more time? Okay, that's probably the most variation I've ever seen between solutions. 20 milliseconds, 20 milliseconds, 17 milliseconds, a full second, almost a full second. Okay, this is quite a thing, huh? All right, definitely should look at the solutions. So this is one way of doing it. I think this is probably the simplest way of doing it. Pretty hilarious that it gets optimized out, and pretty hilarious that it gets optimized out and you can't. It won't work if you just you try to use this normally. You have to take the address and then dereference it each time. I'm sure there's a better way to do this. I'm just thinking, what else could I do? What are some better options than that? I think what I want is, let's do a Boolean, right? Bool right foo equals false, or something like some Boolean I want to say, and then just say like while it's locked. No. Yeah, I want to use some concurrency primitives to get to do this properly, right? let's use some concurrency primitives. So basically, I want to lock writing foo until it's done, and then I can write bar, right? But the problem is that I might write lock foo and write it, and then unlock, and then write the next foo. Right, I've got to switch between locks, I guess, locking foo, and then writing, and then locking bar immediately after foo is locked. But not re-locking foo again. So maybe I could exchange the lock. Maybe I can make the lock a maybe I lock here and I don't unlock until there. How about that? I don't know if that's very good, but you could try it. I could try it. So print foo. I'm gonna mute.lock, then unlock over here. Something like that. It's quite a question, I have to say. Synchronization primitive that can be used to protect shared data. Okay. Alright, lock, unlock. Locks if the mutex is not available. Okay. So we're gonna lock and then unlock. Is that it? But I don't want to write unless the mutex is unlocked. Or no, this doesn't work, does it? So the issue here is I want to lock and then write foo, and then I don't want to write foo again until I've unlocked. But the problem is that as soon as I write bar, I can write bar. I don't want to write bar until I've written foo as well. We have two locks, lock one, lock two, mute one, mute two. Maybe that's the way to go. Mute one, lock, mute. Whoa. Two different mutexes. And this is mute two lock. Mute two unlock. So we lock mutex 1 and mutex 2. This doesn't make sense, does it? I'm thinking lock the first mutex, lock the second mutex, and this is only going to unlock the first mutex. No, they unlock each other. You know, I think it's got to go the other way around, right? No, this doesn't make sense either, does it? No, it doesn't. Oh my goodness. What if I use two mutexes? It's like, no. That doesn't work either. No. This is very funny. It's very entertaining. Okay. Okay. Oh boy. Oh. Take a deep breath, man. Boy, oh boy, oh boy. Oh. Excuse me. So I don't know. I don't know. I want to lock foo, And I don't want to unlock this until I've written bar, right? But I don't want to write bar until I've written foo. So maybe I do need 2 mutexes. Let's try with 2 different. Let's try with 2. See what happens. So we'll lock 1, lock 2, write foo, and then I can unlock 2, right? And this doesn't print until we unlock 2. Yeah, this won't print until we unlock 2. But we don't want to print 1 either as well until, yeah, something like this is what I'm after. So lock 1, end 2, lock 1, end 2. This is so confusing. I don't think this works, quite frankly. I don't really have a way to guarantee that one triggers before the other, right? Yeah, that's probably the first thing. So I lock both mutexes, then and this tries to go 2, then 1. This gets stopped at 2. Waits at 2. Then I unlock 2, and this is still waiting for 1. So no, that doesn't work. What if I just unlock both of them? Well, that doesn't make sense either. No, this doesn't work. Let's just see what happens if I just do one lock at a time. This is pretty funny. It's like, this isn't gonna work, is it? This doesn't make sense. Gee, I'm tempted to just look at the discount. Yeah, just TLEs. Okay, just flat out. It just outright TLEs. Really only need like 2 to test this. Oh, of course. Wrong answer. FooBar bar foo. Okay. Yeah, because the bar can just print whenever, right? I don't know. I want to say some kind of locking is what I want. Some kind of locking. Gee. Could definitely use a lock guard to make sure I print the whole thing before the next thing prints. Right? That's for sure. But excuse me, how do I like, yeah, I would want to lock here until this prints, and then this prints, and then this becomes unlocked. But the problem is that this could print before this, while this one's getting locked again. This could print again. Maybe I want to lock another one. So maybe I'll try to lock this one before it prints, and this one doesn't unlock until the other one prints. Maybe that's the way to go. So I lock M1 and lock L2, M2, and I print foo, and then I print bar, and I don't unlock foo to print again until bar is finished printing, right? So when I try to print foo again, it'll still be locked until bar is finished. And same thing on the other side, when I try to print bar again, M2 is still locked until foo is finished printing. Is that what I want to do? That seems kind of a little awkward. Maybe that's the way to go. Oh, that works. No kidding. It's that simple. Pretty sure this is not a correct answer though. because there's no guarantee which one prints first. Oh, maybe I'm wrong. This game is hard. Okay. This is hard. 1,000, 500, 20, 200, some random stuff. 9.5, 334. Okay. Do I just submit this? Of course. I mean, of course. It's like, really? Of course, that's what. Yeah, I mean, you know, obviously, that's how this is supposed to go. Submit that a few times. Definitely should read the solutions. Oh, 100%. Fastest solution on the site. Absolutely. Every time. This shouldn't work. This definitely shouldn't be correct. It's definitely shocking that this is correct. So 1, 2, 3. Third one is 29 milliseconds. All right, let's do a couple more. Oh, 100% again. Okay. So sometimes it's very fast. Sometimes it's very fast. I can't believe this is right. Like, this can't be right. This can't be right. One more time. It's kind of addicting to try to roll like the much. This is definitely faster than the other idea. It's definitely faster than the other idea. Definitely an improvement on the other idea. I'll say that for sure. Other idea was maybe a little bit much. So yeah, I got to learn more about concurrency primitives, I guess, and how and when to use them. But the basic idea. Yeah, it's pretty fast. It's pretty good. It's reasonable. It's just quite a thing. So my question is, where is the guarantee that this M1 is going to lock before M2? Right? Like, how come bar doesn't print before foo? Right? Because it could, in theory, it could get this, like, yeah, they're alternating, but it could be the other way around, where bar is prints first, right? We lock them both, and then bar comes first before foo, and then I don't unlock. Then I unlock foo, and foo unlocks bar, then foo, and they both basically unlock at the same time, and then bar, they both lock again, and bar prints again, right? Like, why wouldn't it be bar and then foo each time? Because if bar locks M2, then foo, it doesn't unlock until foo prints, so we can't print bar twice. So bar has to wait for foo to print. And foo after bar prints is unlocked, so foo can be printed again. So we have bar that prints, unlocks foo, which we locked foo and then unlocked foo, right? And then foo prints, unlocks bar, which bar is waiting, prints again. While that's going, foo is locked. It's so confusing. This is so confusing. Why does this work? It feels like this definitely shouldn't work. Also, it feels like probably I would get a deadlock at some point too here as well. How does this work, man? I don't understand. How is it possible? if bar locks first, so bar locks M2, prints, unlocks M1, and is waiting to print bar again, it can't print until foo unlocks. Okay, let's say foo got its lock and printed foo, so bar and then foo, and until foo is printed, M2 doesn't unlock, so then M2 is ready for bar again. But bar would unlock M1. Right? Well, they're both trying to print at the same time. So foo is trying to print, bar is trying to print. Foo is locked by 1, bar is locked by 2. Let's say bar is faster, so bar unlocks for foo, bar prints, foo then also prints. Now we couldn't get bar printing twice because M2 is locked. So when bar prints and gets back to M2, it has to stop. Foo, on the other hand, is unlocked on M1. It prints, unlocks M2, comes back to M1. Bar is now printing, unlocks M1. Well, and M1 is locked while foo is printing. So basically, it's just kind of. I think, I'm pretty sure the way the sequence is set up. Like if I just waited a few moments. Like if I just put a wait here, right? Like a sleep. I slept for like half a second, not even, a few milliseconds. I bet that I can get this to reverse directions. Sleep 4. Standard thread, this thread, sleep 4. Let's say 2 milliseconds, or 1 millisecond. Or not even millisecond, like, can I do nanoseconds? Chrono duration, sleep 4. I do like microseconds. I've got these symbols, literals. Oh, there they are. US is microseconds. Okay, microseconds. So yeah, I want like a few microseconds. Let's do like 100 microseconds. So I think that's all I need. If I just let this sleep for 100 microseconds, I think that'll force the other. Yeah, there we go. That's exactly what I was looking for. Boom. Now it's doing bar, foo, bar. Yeah, that's exactly what I thought would happen. It's a few more than 100 microseconds, so maybe I need like 300 microseconds. Yeah. Still, we'll sometimes go foo first. It's gonna be quite a few microseconds, huh? Jeez. Takes a while to start a thread, I think. Huh. How many microseconds do I need? A millisecond, like a full millisecond? Gee. Okay, there we go. So, yeah, basically it works, but it only works because it takes a few microseconds to get the, like either thread could be started first. That's exactly what I was saying. I was thinking, I was like, I'm pretty sure you could reason this out and show that basically, I mean, well, really it's the same code, right? It's symmetric. you know, there's symmetry here. That's probably the reasoning I should have used, because I was trying to think it through like without using symmetry, but because there's symmetry, it's obviously it could go FooBar or bar foo. The only thing that really makes it clear which one starts, guarantees the starting, you know, whichever one goes first, it comes from whichever one takes longer to initiate, whichever one gets initiated first when the threads are created. So it's kind of no guarantee really that bar is going to come second, although it seems to work. It seems to be good enough of a guarantee. How can I make sure that that race condition never happens, that bar always is the second thing that gets printed? Maybe I could use a third mutex. Yeah, because this is a faster solution, but it's not a correct solution. The other solution was always going to be correct, regardless of which thread comes first, and then begins printing first. Whereas this is a faster solution, but it takes on the risk that bar technically could get, for one reason or another, get initiated a little bit sooner and executed a little bit sooner, which is not likely, but it's technically possible, right? There could just be some delay for some reason on the hardware side or whatever, some reason that this took longer than normal. At least in theory, it's possible. Or the person calling this could just reverse the two threads, starts of the threads, and that's the end of that. Reverse the order of the threads. Gee, how do you handle that? That's a good question. I'm not too sure. Maybe this also has to lock M1. No, it can't. It can't lock M1 because it can't lock M1 because if they both try to lock M1, then they're both basically waiting on each other. Oh man, this is awkward, huh? Yeah, you could definitely have a race condition if you don't do this properly. But how do you do it properly? How do you do this properly? What do you mean? Excuse me. Maybe do it this way. Maybe to guarantee that this happens after this one, you have a lock, right? Another lock. M3. And you lock it here. And you lock it here. Right? And this one never unlocks M3. This one is locked. Only after foo is printed is M3 unlocked. Right? We just say if I is equal to 0, unlock M3. And this if statement should get branch predicted out. Yeah, so they both lock. But if no. No. I don't think the mutex can be used for this. No. that doesn't work either. Because you could lock bar first. And then you have to unlock. It never unlocks for foo. Excuse me. I don't know, man. How can you guarantee one or the other? Could use locks to control their relative order in this way. This just guarantees that one has to follow the other alternately. It doesn't guarantee which one comes first. I don't know, man. I don't know what to say. It's a tough one. That's a tough one. Excuse me. I mean, could do this. This is like, oh boy. Do this again, huh? Check equal to true. So it's, yeah. Let's do it all the way around. So start with true. Don't enter this loop. Have a guard busy loop for a few moments. And the first thing this will do when this is called, it'll set check to false. And this should break here. So this will wait until this foo is printed, until this routine occurs. Now we don't need any of these. But that one. I don't like that idea, but that works. Let's try that one now. Not a good idea, but now this one's correct. It's slower, I think. By the way, this is I think this gets optimized out. Oh no, it's still correct. Okay. Maybe a little bit better. Okay, slower. Seems to be substantially slower. Okay. A little bit slower. But correct now. Definitely correct now. I did it. Figured out a way to make sure it's correct. Yeah, you can't be having race conditions like that. That's not gonna work. Alright, it's substantially slower, but doesn't rely on it's substantially slower, but it doesn't rely on the order that you execute the threads in. Like even if you call this thread first now, and then this one shortly after, it's gonna wait before it begins. Okay, interesting. Very interesting. I just keep submitting to see how fast it's gonna be. Yeah, so if you really want a lot of speed, you could just remove this altogether, and now it goes really quick because you're basically assuming, you're just assuming that it's going to print foo first. which it almost always does. So could take some risk for data races, and you'll still be correct and fast, or not correct, but you'll be fast. Could take some risk for data races, and you'll be fast, but could be wrong in some instances. There we go. Yeah, it's the fastest possible. Does what was described. But if you want it to be correct, always correct, this is one way of doing it. This will basically guarantee one thread waits in a busy loop until the other thread is ready. Oh, I get 100% anyway. Oh, okay, never mind. They're about the same speed. I take it back. I take back what I said. This is correct and fast. Okay. They should also actually this actually should be over here. This is actually the wrong spot, I think. Should really be after foo is printed. I mean, you really don't need to go, well, yeah, okay. Maybe this is actually more correct. Technically not correct, the other approach. Should get branch predicted out. You still could technically have the data race with what I just described. It's just a lot less likely. Yeah, because this would be basically would set that variable and then begin the for loop, while this one is hasn't even begun its for loop, so it kind of guarantees that it'll be faster, but actually, in theory, technically speaking, it still could be incorrect. I think this is the only way to make it absolutely correct, because now you got the locks going at this point with this check in here. Still pretty fast. I wonder if I could just always just repeat this over and over again. I think getting branch predicted is probably pretty good. Wondering now. It's faster or slower if I just set this variable every time. It's also a lot of submissions. Just want to see how fast it'll go. Yeah, okay. I think the branch prediction is better. Keep saying this is correct or not correct. I think it's like kind of a lot of variation here. Oh no! Oh! Was I wrong? Was I wrong? Uh-oh. Uh-oh. Wait, no, what? Huh? Wait a second. What? Oh no. Wait, what happened there? No. What is going on? Oh man. Oof. Oh. What did I do? I TLE'd again. What? But that's not supposed to. Did it get opted? No. What? No. This is crazy, man. I don't know what happened. I don't know how that happened. It like deadlocked. Oh, that's bad. Oh. Oh, I don't know. I don't know. There we go. Okay. So, okay. I don't know what to say about this. This is a lot of I don't knows. So I don't know how I got a TLE. I don't know how that's even possible. Somehow I got a TLE. I couldn't tell you why, but yeah, I mean, can't enter this block without going through this one. And yeah, M1 should be unlocked. M1 should be locked and M2 unlocked by the time this opens. And M2 should be get locked here, and M1 unlocked. I don't know how this could get a deadlock. I don't know how that's even possible. Somehow it deadlocked before. This is one of the reasons why I prefer lockless programming, because it's just like how do you even figure out that this can deadlock? So I think this is correct, because it's not possible, and it may have been in some kind of optimization or something that happened before where it deadlocked. I think it deadlocked here. I don't know why it would do that or how it would do that, how it's possible for this to deadlock. Because these don't deadlock. This alone shouldn't deadlock because it's only locking and unlocking. Unless you get like a double printout somehow. But you can't get a double printout because the thing, it's the other thread is what unlocks to print the next element. So it's not possible to double print something, right? So once you've locked M2, you can't print again until it's unlocked on the other thread, and same thing. Once you've locked M1, you can't print it again until M1 is unlocked on the other thread. So you're gonna just lock and unlock back and forth. What could happen is, well, yeah, this is locked by the time this one is even executing. So the only thing that could really happen is maybe this check is skipped somehow, which it shouldn't. It shouldn't. And again, there was some kind of compiler optimization that we had an issue with. Maybe that was what it was. It got optimized out. I didn't realize it got optimized out, and I didn't realize it got optimized out, and I was just basically running this without this check at all. That must be it. I didn't realize. And something like that, I don't know. I don't know if that would cause us deadlock, but maybe. I don't know how it's even possible. I don't know. All right, let's look at some of the solutions. Yeah, it's a good question. This is a pretty tough one, quite frankly. It's a pretty tough one. All right, let's do most votes. 5 Python threading solutions. Barrier, event, condition, lock, semaphore with explanation. How do you use a semaphore for this? Semaphore, C++, mutex, and CV. Super simple using 2 semaphores. Semaphores. Boolean volatile. Atomic mutex semaphore. Okay, here we go. Time to learn. Barrier, event, condition, lock, semaphore. Raises a barrier which makes both threads wait for each other before they're allowed to continue. Foo prints before reaching the barrier. Bar prints after reaching the barrier. So barrier. Okay, I don't know what barrier is. First time I've seen that before. What is that? Oh, it's real. Look, it's a real thing. Standard barrier is a thread coordination mechanism that blocks a group of threads of known size until all threads in that group have reached the barrier. Unlike latch, barriers are reusable and execute a possible empty callable before unblocking threads. A barrier object's lifetime consists of one or more phases, each defining a phase synchronization point where waiting threads block. Threads can arrive at the barrier but defer waiting on the phase synchronization point by calling arrive and later block on the phase synchronization point by calling wait. Latches and barriers are simple thread synchronization mechanisms that enable some threads to wait until a counter becomes 0. In C++, 20 latches and barriers will be available in 3 variations: latch, barrier, and flex barrier. Okay. All right, so these are pretty good, these primitives. I'm not extremely familiar with these things, but yeah, now I'm learning, I guess. This is why I practice. Barrier. Oh, it's the header. Okay, I don't need the header. I need the barrier itself. There are all kinds of atomic things here too. Okay. Latch and barrier. These are relatively new. I mean, they're a few years old now, but they're not beyond C++ 17. Latch class is, oh, let's do barrier. Let's do this one first. Yeah, the class template standard barrier provides a thread coordination mechanism that blocks a group of threads of known size until all threads in that group have reached the barrier. Okay, blocks a group of threads of known size until all threads in that group have reached the barrier. Unlike latch, barriers are reusable. Once a group of arriving threads are unblocked, the barrier can be reused. Unlike latch, barriers execute a possibly empty callable before unblocking threads. Interesting. A barrier object's lifetime consists of one or more phases. Each phase defines a phase synchronization point where waiting threads block. Threads can arrive at the barrier but defer waiting on the phase synchronization point by calling arrive. Such threads can later block on the phase synchronization point by calling wait. Not sure what that means. Barrier phase consists of the following steps. The expected count is decremented by each call to arrive or arrive and drop. When the expected count reaches 0, the phase completion step is run, meaning that the completion function is invoked and all threads blocked on the phase synchronization point are unblocked. The end of the completion step strongly happens before all calls that were unblocked by the completion step return. Exactly once after the expected count reaches 0, a thread executes the completion step during its call to arrive, and drop, or wait, except that it is implementation defined whether the step executes if no thread calls wait. So you can actually read this with me. When the completion step finishes, the expected count is reset to the value specified at construction less the number of calls to arrive and drop since, and the next barrier phase begins. Concurrent invocations of the member functions of barrier, except for the destructor, do not introduce data races. Okay. Interesting. Template parameters. Okay. Completion function, a function object type. Completion function must meet the requirements of move constructible and destructible. Is no throw invocable must be true. The default template argument of completion function is an unspecified function object type that additionally meets the requirements of default constructible. Calling an L value of it with no arguments has no effects. Calling an L value of it with no arguments has no effects. Every barrier object behaves as if it holds an exposition only non-static data member at completion underscore of type completion function and calls it by completion underscore on every phase completion step. Okay, I don't fully understand what I'm reading, but that's fine. Arrival token, an unspecified object type meeting requirements of move constructible, move assignable, and destructible. Constructor constructs a barrier. Destructor destroys the barrier. Operator equal barrier is not assignable. is deleted. Arrives at the barrier and decrements the expected count. Wait blocks at the phase synchronization point until its phase completion step is run. Arrive and wait arrives at the barrier and decrements the expected count by 1, then blocks until the current phase completes. Arrive and drop decrements both the initial expected count for subsequent phases and the expected count for current phase by 1. Arrive and drop. Constants maximum value of expected count supported by the implementation. Okay. Interesting. So workers, Anil, Bosara, Carl. On completion, no except. Locking not needed here. Phase done, cleaning up. Okay. Phase sync point, S size. Workers, what is this? Finding these headers. Size of the given range. C.size. Why? What is this? Where did this come from? I don't remember seeing. I don't remember this. C++ 17, 20. What is this? Where did this get added? I feel like I should know when this got added. I should probably look at the standards to see exactly when it got added. Signed integer equal to the size of a range. Okay. Since C++ 20, the signed size is available. Oh, okay, that's cool. I like that. Neat. Oh, cool. Works with containers, built-in arrays too. Oh. C-style arrays. It works with C-style arrays. That's kind of neat. I like that. I'll start using that. Nice. Cool. Okay. It's in 20 though. Okay. Strongly happens before regardless of threads. Evaluation A strongly happens before evaluation B. If any of the following is true, A is sequenced before B, A synchronizes with B, A strongly happens before X, and X strongly happens before B. So it's transitive. A is sequenced before B, A synchronizes with B, and both A and B are sequentially consistent atomic operations. A is sequenced before X, X simply happens before Y, and Y is sequenced before B. A strongly happens before X, and X strongly happens before B. Note, informally, if A strongly happens before B, then A appears to be evaluated before B in all contexts. Note, strongly happens before excludes consume operations. Yeah, it gets really confusing. Some things are atomic, some things are not, some things are... It's pretty involved, huh? Yeah, I think when you start combining concurrency with smart pointers, it gets really complicated. It's one of the reasons I don't really like smart pointers that much. I don't really like concurrency that much either. Lockless concurrency I think is good, but sometimes that's not that realistic. Okay. Boy. There is a lot to go over here, huh? Memory order, yeah, okay. So much reading to do. There's definitely a lot of reading I should do. Too many things to work on, huh? Arrive and drop, okay. Decrements the initial expected count for all subsequent phases by 1, and then decrements the expected count by the current phase by 1. This function is executed atomically. Call this function strongly happens before the start of the phase completion step for the current phase. Behavior is undefined if the expected count for the current phase is 0. Okay. Interesting. Notes can cause the completion step for the current phase to start. Current expected count is 0 before calling this function. The initial expected count for all subsequent phases is also 0, which means the barrier cannot be reused. Arrive. Okay. So yeah, size is fine. Oh, barrier. Okay, got it. Sync point, size of the workers on completion, work, string name, starting, threads, threads reserve, size workers. That's fine. For each workers and place back worker. Okay, that's fine. So this starts all the threads, right? What's the sync point? Where's the sync point? Oh, work. Oh, it happens during the work they're doing. Okay. Worker. JThread. What is a JThread again? I don't use this very much either. Single thread of execution has the same general behavior as thread, except that JThread automatically rejoins on destruction and can be canceled, stopped in certain situations. Threads begin execution immediately upon construction of the associated thread object, depending on any operating system scheduling delays. Starting at the top level function provided as a constructor argument, the return value of the top level function is ignored. And if it terminates by throwing an exception, terminate is called. The top level function may communicate its return value or an exception to the caller via standard promise or by modifying shared variables, which may require synchronization. See standard mutex and standard atomic. Unlike standard thread, the JThread logically holds an internal private member of standard stop source, which maintains a shared stop state. The JThread constructor accepts a function that takes a standard stop token as its first argument, which will be passed in by the JThread from its internal standard stop source. This allows the function to check if stop has been requested during its execution and return if it has. Standard JThread objects may also be in the state that does not represent any thread after default construction, move from detach or join, and a thread of execution may not be associated with any JThread objects after detach. No two standard JThread objects may represent the same thread of execution. Standard JThread is not copy constructible or copy assignable, although it is move constructible and move assignable. Okay, I'm not entirely sure what to make of this, other than it looks like I need to learn more about concurrency. New JThread object. So the reason why one of the things I'm thinking about, wondering about is, suppose you have a thread, let's call it a JThread, and you want to execute a sequence of other threads from that thread, right? You basically want to run threads recursively. So you have one thread, let's say you start 10 threads, and each of those threads are supposed to run 10 other threads and wait to join on those other threads. I guess my question is, can you do that with a JThread? Because I think if you start the other threads and then finish execution, it'll automatically join while the other threads are still going, which I think will cause problems depending on how you're operating, how you're doing things. Yes. Yeah. I think you can wait on the other threads. Does the standard thread not always join? What does it mean to JThread automatically rejoins on destruction. Do these threads not automatically rejoin? What does it mean for the thread to automatically rejoin? Auto joining and cancellation. What does that mean? As opposed to what? Thread represents a single thread of execution. Threads allow multiple functions to execute concurrently. Threads begin execution immediately upon construction of the associated thread object, pending any operating system scheduling delays, starting at the top level function. Provided as a constructor argument, the return value of the top level function is ignored. If it terminates by throwing an exception, standard terminate is called. The top level function may communicate its return value or an exception to the caller via standard promise or by modifying shared variables, which may require synchronization. See standard mutex and standard atomic. Standard thread objects may also be in the state that does not represent any thread after default construction move from, detach, or join. And a thread of execution may not be associated with any thread object after detach. No standard thread. Two standard thread objects may represent the same thread of execution. Standard thread is not copy constructible or copy assignable, although it is move constructible and move assignable. Represent the idea of the thread. Joinable, potentially running in parallel contexts, get ID, native handle, hardware concurrency. Join, waits for the thread to finish its execution, detach. I think the J thread can be automatically rejoins on destruction and be canceled, stopped in certain situations. I think what this implies is that in this context that I saw it in, this point here, this destruction here, these threads will be destroyed, these threads are joined. I think that's what it means. Yes, it means that it's automatically joined at the end here, which is typically what you do when you want to run threads of execution, is that you don't actually want to, like, you want to join all the threads before you finish finish your execution. So yeah, if you ran 10, let's say 10 threads, excuse me, each of which, and they were J threads, each of which ran another 10 J threads, the J thread object, when it goes out of scope and destroyed, is joined. That's what that's referring to. So when this vector goes out of scope and the J threads go out of scope, then they'll all be joined. Yeah, that's fine. Now the question is, if you run a thread which runs 10 more threads, right, or 10 threads that each run 10 more, the next round, the second level of threads running, the first 10 threads are running some execution, and each of those execution blocks of code, those are running 10 more each. So you've got 110 threads. And then each of those blocks that are running those threads, it's going to wait automatically for that block. It's going to wait for all of those other threads before the block finishes. And then when the block finishes, then the execution is complete, but it's not until you go out of scope that that other thread is going to join. The question is, can you join the first thread? Let's say now let's just do one thread that calls 10 other threads. The first thread that calls 10 other threads generates 10 other threads. Once it's finished generating the other threads, it's going to join. I'm sorry, the main thread. There's like three levels. There's the main, a single thread, and then a thread that thread creates 10 more. Main, once it creates that thread, it's going to join on that thread and wait for it to complete. That second thread, though, all it does is create the other 10 threads and joins those, waits for those to complete. So it doesn't finish. So the main thread waits for the second to finish. The second finishes when the other 10 complete. Yeah, it's fine. It works. It's confusing, but it works. You just have to have joins. Joining. I'm pretty sure it works. It's just I've tried to practice that in code at home, I guess we'll say. Well, I'm always at home, I guess, but yeah, I had an interview where they gave me a take-home assignment. I tried practicing that, and I was getting very confused because I think I couldn't tell if the program if it worked the way that I described. It's like kind of hard to think it through. It's like it seems kind of simple, but at the same time, it's not that simple. It's not that obvious that it will definitely be okay because you join layers of joined threads. Basically, is the idea. Should work in theory, I think. Anyway, the sync point here is the interesting part. Workers on completion, osync stream. Oh, look at that. Whoa, that's a new one for me. It's atomic. Oh, I see. Okay, that's probably what osync stream is supposed to do, is use atomic operations. The sync point, arrive and wait. Okay. So this will wait for this work. Each of these threads, it'll sync at this point, at the barrier. It syncs here too. Syncs here and then syncs here. That's really cool. So you can have synchronization within the threads. And the size is going to be all the workers. Okay. And on completion, it'll done cleaning up phase. Phase equals this string, print this, and then set it to done. So done cleaning up, and then done again. So it'll initialize once, done cleaning up, and then when it's called again, it'll print done. So it'll be done cleaning up done. So it's worked first. Everybody worked. They're done cleaning up, and then now it's cleaned, and the second time this prints, second phase, it'll print done. That's cool. That's very cool. Amazing. I don't know what else to say here. Okay. I think I get it. Arrives at the barrier and decrements the expected count by 1, then blocks until the current phase completes. Decrements both the initial. So on completion, I think it blocks until it executes this line of code. Decrements both the initial expected count for subsequent phases and the expected count for the current phase by 1. Oh, that's interesting. So it drops a doesn't just drop the expected, so it arrives and doesn't just decrement the expected count, but it also decrements the initial expected count for the subsequent phases. Okay, that's interesting. I guess in some cases that's useful. Decrements the expected count, blocks until for current phase completes. Oh, excuse me, these don't block. This will block until the phase synchronization point, until its phase completion steps run. Oh, I see, okay. So this will block, this will arrive and decrement the count, this will decrement the count and block, and then this will decrement the count, and drop the expected count, I think, for the rest of the phases. That's interesting. Construct the barrier, destroy the barrier. Okay. Very interesting. I think I understand. I think I get it. Latch is a little bit different though. Latch is, I think I understand what these do. Yeah, JThread is probably what you typically want rather than thread. And it looks like you can stop source, stop token, request stop. That's kind of interesting. Apparently you can stop the threads. To look at that later. Construct a latch. The latch class is a downward counter of type pointer diff, which can be used to synchronize threads. The value of the counter is initialized on creation. Threads may block on the latch until the counter is decremented to 0. There is no possibility to increase or reset the counter, which makes the latch a single-use barrier. Concurrent invocations of the member function standard latch, except for the destructor, do not introduce data races. Interesting. Unlike standard barrier, standard latch can be decremented by a participating thread more than once. Oh, okay. Cool. Constructs a latch, destroys the latch. Latch is not assignable. Decrement the counter in a non-blocking manner. Test if the internal counter equals 0. Blocks until the counter reaches 0. Arrive and wait decrements the counter and blocks until it reaches 0. Okay. So name, product not worked, action, job, jobs, Nika, Baru, Chuck. Latch work done, latch start cleanup, size jobs, work, job, my job, work done, cleanup, job, product cleaned, work is starting, reach the jobs, job.action equals thread work, reference job, work done.wait, reach the jobs, product workers are cleaning up, done, okay. Work is starting, done, Anika, Baru, and Chuck worked, workers are cleaning up, Anika, Baru, and Chuck cleaned, okay. So where's the latch? Latch is the work done, and there's a start cleanup. Latch of size 1. And so here we have the work, which is worked, and clean up. So work done.countdown, and then start cleanup.wait. So you wait for this latch and all of these threads. Okay. So work is starting. We count down the work done latch. Which I don't think. Oh yeah, we're waiting until all these threads are done, or at least all the threads reach that point. And then we say it's done, and then now we say for each job, we print the job name worked, job name clean, jobs. I think there's 1, 2, 3 jobs. Oh no, I see. Okay, the name, the product, the action. Okay, I get it. This is interesting, actually, how they're setting this up. The array by default, the struct just one name. The others are already pretty okay. So that's kind of interesting. Threads are created automatically, huh? Job.action. Well, they're empty threads, right? Not associated with anything. So we create this thread with work and a reference to job. What is this? This is a reference wrapper, which I think is needed in some cases. It gets kind of confusing why and when you need it, but it typically has to do with bindings and, well, let's just say bindings. Thread, what is, why does this have 2 function the arguments? Oh, I see. Oh, I didn't see that. Okay, that makes sense. Yeah. That's why it needs the reference. It's being used as a, basically as a binding. When you create the thread. When you have certain functions, typically constructors that use a what do they call that? I guess it's R value reference is the, what's that called? It would be like the R value reference for, it's not a fold expression, it's a parameter pack. Yeah, typically when you have R valued parameter packs, usually for constructors, you would have to pass a reference or C reference wrapper to the argument in order to properly handle that, which is a strange thing. It seems to be true for threads and for binding. Thread and bind both use that. Yeah, because it's using a forward. Yeah, forwards the type. Yeah, forwarding a reference. Forwarding reference. Make sure it has the right value category. Yeah, arg is always L value. Forward is L value or R value depending on T. Interesting that arg is always L value, even though it's an R value reference to T. Very odd. I don't really know how that works. I don't really know. But bind should be somewhere here. Yeah, bind also uses this style of R value references as a parameter. So you've got to use forwarding. Yeah, all that's like related to the forwarding and a reference wrapper and so on. It's typically when you'd use that. Anyway, pass by reference, pass by value, right? So the reason why you'd want to do this is because you're calling work with these parameters, which is the job itself gets passed to it. I like this way of doing it. This is pretty good, actually. I didn't really think about that. You could do it that way. Just make a reference to the object associated with that thread as a parameter to the thread. Keeps things simple. Interesting though that it's like same object holds the thread that's operating on itself. Something about that's kind of peculiar, but it makes sense. But it's like a weird way of thinking about it. Yeah, and then it's modifying the product, which is then called work done dot wait done print all the working they did, and then next start cleanup and countdown, which should go down to 0, and then these threads should then change appropriately. Join all the threads, so it's all done, and then these are not J threads now. And then now that they're all done, we know that the product values have been updated, so we can call them all. Very interesting. Good example. Shows a lot of stuff. Also here is kind of interesting that these objects can be created with just the name as the parameter, and it's just like the default behavior of a struct works in that way. It's pretty cool. So there's this things. Those are some things you could do with a latch. It's a little bit different than a barrier. It's like a one-time use barrier. That's kind of cool. All right. So we have latches, barriers, and then we have semaphores, which I don't totally understand use case of the semaphores, but I guess we'll find out a little bit more now. Lock guard is just to make it RAII style. Okay. All right. Back to, this is a lot of time spent thinking about this, but yeah, I mean, I spend a lot of time doing other things. I tend not to, there's a lot of things I don't get around to, quite frankly. Raise a barrier which makes both threads wait for each other before they are allowed to continue. Foo prints before reaching the barrier. Bar prints after reaching the barrier. Okay. So we have barrier 2, print foo, wait, barrier, print bar, wait. Count the number of times foo and bar was printed and only print foo if the number of times is equal. Bar prints if foo is printed fewer times. Use condition and wait for it to synchronize the threads. So there's a condition as well. This is kind of what I was trying to do before, but I didn't use any of these primitives. Let's see if this exists in C++. I'm sure it does. Condition variable, yeah. Okay. So how do I use barrier? Let's try barrier. Let's try barrier. How can I do this? So create a barrier size 2. Just call it B. And what did he suggest? What did he do? He said let's look at barrier again. So this creates a synchronization point, the barrier. So we can arrive and wait here. So let's try a barrier. I don't print foo first and arrive and wait for it to print bar, and then bar, I don't print bar until I've printed foo. So they both arrive and wait, print foo, then after I printed foo, I basically stop waiting here. The barrier drops and I print bar. When does the barrier get reset? How does the barrier get reset? Sync point. Okay, after, so it gets reset immediately, I think. As soon as they've synchronized, so foo, and then this synchronizes at before bar, right? So it's after foo and before bar. Then bar could be printed, the barrier gets reset to 2. Now I try to go to the next sync point, which is going to be 2 becomes 1. Foo has to be printed, and then this has to sync up again. So yeah, it kind of goes back and forth, I think. I think it's that simple. It's just standard barrier. This compiler is too old. Never mind. expected. Never mind, it's not the computer. No, it's my fault. Never mind. That's my mistake. It's not the compiler's tool. This is just an empty function, I think. Just doesn't do anything, I think, at the synchronization point. Excuse me. What? Oh, maybe it is the compiler, I don't know. I think the compiler version is 17. Yeah. Parameter declarator? I don't know if that matters. Can I use a barrier? I think the compiler is too old. I don't know. Let's see if this compiles. Hold on. It could just be that the compiler's too old. I could print. There's a way to print the compiler version. I'm actually looking for compiler version built in. Oh man. Feature testing. Language features. Yeah, macro. There's like a macro, something, a dunder. I forget what these are called. Macros, dunders. Dunders are just a double under. Dunder strings with macros. Okay. Certain built-in. There we go. C++. That's the one that I want. Yeah. Dunder C++. Okay. I think the compiler version is too old to use. 2020-02. Oh. Maybe it does have barriers. C++ 20. Oh, there you go. Cool. Yeah. Should be able to use barrier. Why can't I use barrier? Sync point size on completion. Okay. Interesting. 2 and basically an empty function. Okay, I'm not sure why I would need to include this, but maybe I do. It's a little weird, but all right. Template arguments, not allowed in non-static class member. No. Oh, okay. Maybe that's why. That's why it wasn't found in standard. Didn't realize this was templated. Okay. Class completion function. Barrier. Void, basically. Come on. Okay. Must explicitly initialize the member B. Does not have a default constructor. Doesn't have a default constructor. Okay. Does that work? Parameter declarator? It's killing me. Why is it so complicated? Oh, why? Okay. Excuse me. It's not copy, it's not assignable. Oh no. Can only be constructed. That makes things a little more complicated, huh? Parameter declarator. I don't really know what that means exactly. It's not copyable. Excuse me. Okay. Data member. Need some help. I don't know. I don't want to spend too much time thinking about this. It's like more complicated than it needs to be. Oh. No. Excuse me. Oh. what a headache. I just want. How? What's going on here? This is like. This is kind of ridiculous. How do I? How is this supposed to work? Can I do this? I don't think so. How do? Explicitly initialize a member. Reference initialization. Excuse me. Feels like I need to use an initializer list to do this. So I was trying to do this, but I couldn't quite do it. Yeah, it's a bit awkward, huh? Excuse me. Wow. Gee. Huh. How am I to do this? Oh. Oh, this is difficult, huh? Could try to use a member initialization list, but it seems. Excuse me. I don't know how to do this. This is new to me. Oh, it compiled. Wrong answer, but it compiled. Well, gee. No kidding. You know, I don't know what to say about this. I don't know. How? Hmm. Hmm. Okay. Is this what I just read? Class members, which are classes, then avoids an unnecessary call to a default constructor. Yes, so that's the problem that I have right now. I literally can't call the default constructor, right? If I do a public a x0 a int x, okay, and b a dot x equals 3 a, okay. Constructor for b will call the default constructor for a, then initialize a dot x to 3. Better way would be for b's constructor to directly call a's constructor in the initializer list. Call it here, right? ba3 would only call a's int constructor and not its default constructor. In this example, the difference is negligible, but imagine, if you will, that a's default constructor did more, such as allocating memory or opening files. You wouldn't want to do that unnecessarily. Or, I think in my case, when I try to set a variable, let's say this doesn't have a constructor or something, like its default constructor basically makes it empty, and I need to, like a thread, for example, right? When it's empty and not associated with any thread, then I need to create the object and associate and basically point this variable, associate with this variable that object. If I could just create this directly, that would be much better. Something like that, like what I'm doing right now is sort of the problem. I don't know how to. What's weird about this though is, like, doesn't this preclude me from like, in this case, the barrier is a relatively simple like object, I guess. So like the parameters are relatively straightforward, but wouldn't this preclude me from like running some logic here to get, I guess I'd have to write another function or something to calculate this number, but that's kind of issue I'm considering now is, like, what about more complicated initialization sequences? And I kind of need to do it this, I don't need to do it this way, but this seems to be the only way that I know how to get this to to initialize without throwing compiler errors. Still wrong though. A lot closer though. FooBar. Okay, cool. So yeah, this is C++ 20. It's just, wait, why is this wrong? FooBar. Oh, okay. It's got some like basically race conditions going on here. Okay, it's not quite correct. It's close. It's really close. So it synchronizes foo and then bar. Synchronizes here to print foo, and then you can keep going to print bar. I think you could just synchronize again. Oops. Right. So synchronize before. So I have print foo and synchronize here. Then print bar and synchronize here. And the same thing again and again. Just keep repeating that over and over. I think that works. There we go. Yeah. That's a really simple way of doing this. Very straightforward. Let's do like 1, 2, 3. Actually, let me undo that. Just make one of these a 1. I like that a lot. That's a very clean solution. That's an extremely clean solution. Very quick. And I learned some things here. Learned about sweet. I like that a lot. That's a very clean solution. I learned a little bit about initialization, questions about initialization that I probably should have known the answer to, but I just never really got around to it. Or what do they call that? More, I guess, detailed understanding of initialization. Isn't as fast, I think, as the other solution that I had, but it's pretty good. It's very simple, very simple. Yeah, I like that a lot. So there you go, there's a barrier solution. Then there's another solution. Interestingly, this was wrong for me. Put the barrier after foo, and before bar. Oh wait. Oh no, yeah, so I did the first time. That was not correct for me at times. This is an incorrect solution. Yeah, it's wrong. It's wrong. Barrier after foo and before bar. After foo and before bar. Wrong. You can fix it though by just adding another synchronization point. And that works fine. It's a little slow, but it's okay. Not the best solution, but definitely a very simple solution. Pretty fast, relatively fast and very simple. Very easy to explain, very easy to code. That's great. Actually, it's a fantastic solution. The next one would be, so I think this is an incorrect solution. Count the number of times foo and bar was printed and only print foo if the number of times equal. Bar if foo is printed fewer times, use condition and wait for IO synchronization. Wait for it to synchronize the threads. Okay, yeah, condition. I need to learn how this works. Excuse me, too. This is kind of what I tried to do before, but I didn't use any IO or synchronization. I didn't use any synchronization to do it. I just kind of did it with like raw, just raw code. Just raw checks on the variables. Just not really the right way to do that. Some part of me was like, this is definitely not the best way to do this, and it was not the best way to do that. I don't know, man. You gotta try things, right? You gotta try things sometimes. Also, I think S size. No, must be 20. Yeah, S size is 20. Cool. I'm looking for condition. Oh yeah, I have that already. So synchronization primitive. All right, here we go. So condition variable class is a synchronization primitive used with a standard mutex to block one or more threads until another thread both modifies a shared variable, the condition, and notifies the condition variable. The thread that intends to modify the shared variable must acquire a standard mutex, typically via a lock guard, modify the shared variable while the lock is owned, call notify one or notify all on the standard condition variable can be done after releasing the lock. Even if the shared variable is atomic, it must be modified while owning the mutex to correctly publish the modification to the waiting thread. Any thread that intends to wait on a standard condition variable must acquire a unique lock standard mutex on the mutex used to protect the shared variable. Do one of the following: check the condition in case it was already updated and notified, call wait for, or wait until on the standard condition variable, atomically releases the mutex and suspends thread execution until the condition variable is notified, a timeout expires, or a spurious wake up. occurs, then atomically acquires the mutex before returning. Check the condition and resume waiting if not satisfied. Use the predicted overload of wait, wait for, and wait until, which performs the same 3 steps. Standard condition variable works only with standard unique lock, standard mutex, which allows for maximal efficiency on some platforms. Standard condition variable any provides a condition variable that works with any basic lockable object, such as standard shared lock. Condition variables permit concurrent invocation of the wait, wait for, wait until, notify one, and notify all member functions. The class standard condition variable is a standard layout type. It is not copy constructible, move constructible, copy assignable, or move assignable. Okay, so, gee, there's a lot going on there. Constructor constructs the object, destructor destructs the object. It's not copy assignable. Notify one notifies one waiting thread. Notify all notifies all waiting threads. Wait blocks the current thread until the condition variable is awakened. Wait for blocks the current thread until the condition variable is awakened or after the specified timeout duration. Wait until blocks the current thread until the condition variable is awakened or until specified time point has been reached. That's interesting. I like that. Native handle returns the native handle. What is that? Native handle accesses the native handle of this. The meaning and the type of the result of this function is implementation defined on a POSIX system. This may be a value of type pthread condition t pointer. On a Windows system, this may be a p condition variable. Underlying implementation defined thread handle. Okay. Both of those for thread and jthread. I don't really know what that means, but okay. So it could be something on POSIX, could be something on Windows. It's okay. Okay. Mutex M, condition variable CV, string data, ready, processed. Worker thread, wait until main sends data, unique lock, LM, lock M, CV.wait, lock, return ready. After the wait, we own the lock. Worker thread is processing data, data plus equals after processing. Send data back to main, processed as true. Worker thread signals data processing completed. Manual unlocking is done before notifying to avoid waking up the waiting thread, only to block again. See notify one for details. Lock unlock, CV notify one. Into main standard thread worker thread, data equals example data, send data to the worker thread. Lock guard, lock M, ready is true. Main signals data ready for processing. CV.notify one, wait for the worker. Unique lock, lock M. CV.wait, lock, return processed. Cout back in main, data equals data, worker.join. Okay. So we call main, have a thread, worker thread. Worker thread is here. Wait until main sends data, we create a unique lock, which I don't really know what that does. Similar thing. Class unique lock is a general purpose mutex ownership wrapper allowing deferred locking, time constrained attempt set locking, recursive locking, transfer of lock ownership, and use with condition variables. Class unique lock is movable but not copyable. It meets the requirements of move constructible and move assignable, but not of copy constructible or copy assignable. Class unique lock meets the basic lockable requirements. If mutex meets the lockable requirements, unique lock also meets the lockable requirements. Example can be used in standard lock. If mutex meets the timed lockable requirements, unique lock also meets the timed lockable requirements. Okay, I don't fully understand these things, but that's okay. Template parameters, mutex, the type of the mutex to lock. The type must meet the basic lockable requirements. Member types, type, mutex type, definition, mutex. Member functions, constructor constructs a unique lock, optionally locking, taking ownership of the supplied mutex. Okay. Unlocks, releases ownership of the associated mutex if owned. Unlocks, releases ownership of the mutex if owned, and requires ownership of another. So this is a lock. Not so familiar with locks. Maybe I should just look at regular lock. So it's a unique lock as opposed to a lock. Lock guard, scope lock, lock unique lock, shared lock. It's very similar to pointers. Like I said, when you start combining concurrency with with memory management, you start getting to like unique locks for unique pointers, shared locks and unique pointers, and all kinds of combinations of things. That gets definitely more confusing than I prefer to think about, quite frankly. But anyway, I guess at some point you do have to think about these things on some level. All right, how are we doing on time? 2.5 hours. All right, yeah, going through all these details here. I mean, this is important stuff that I haven't really looked into. I mean, yeah, if you're just solving, LeetCode style questions all day long and just spending all day thinking about algorithms, most of which almost never are concurrent, you're just never going to look at the concurrency library. Which is kind of the position I find myself. I know about concurrency, but I don't know it that well. So spend some time today familiarizing myself a little bit more. Locks the given lockable objects, lock 1, lock 2, lock n, using a deadlock avoidance algorithm to avoid deadlock. Okay. Oh, it's a lock algorithm. Okay, I see. So things that are lockable. What's lockable? The objects are locked by an unspecified series of calls to lock, try lock, and unlock. If a call to lock or unlock results in an exception, unlock is called for any locked object before rethrowing. That's cool. Boost provides a version of this function that takes a sequence of lockable objects defined by a pair of iterators. Scope lock offers an RAII wrapper for this function, is generally preferred to a naked call to standard lock. Okay, so you can lock, then unlock, and you have a lock guard too. Lock guard, adopt lock. Interesting. Oh, it'll unlock these as well. Deadlock avoiding RAII wrapper from multiple mutexes. Yeah, that's confusing. Standard lock to lock pairs of mutexes without deadlock. Deadlock avoidance algorithm to avoid deadlock. Objects are locked by an unspecified series of calls to lock, try lock, and unlock. Okay. Just locks everything. Okay. Defer lock, try to lock, and adopt lock are instances of empty struct tags. Tag types: defer lock T, try to lock T, and adopt lock T, respectively. Used to specify locking strategies for lock guard, unique lock, and shared lock. Okay. Defer lock: do not acquire ownership of the mutex. Try to acquire ownership of the mutex without blocking. Assume the calling thread already has ownership of the mutex. Okay. Which is when you lock it, already locked mutexes are unlocked at the end of the scope. Okay, I see. Equivalent approach, unique lock, lock. I think both unique locks will unlock them too. Okay. Just what happens here. General purpose mutex ownership wrapper allowing deferred locking, time constrained attempts at locking, etc. Okay. Unlocks the mutex if owned and acquires ownership of another. Lock, try lock 4 until unlock. Swap release, turns a pointer, owns lock, bool, swap. Does this unlock when optionally locking it? Okay, not necessarily locking it. Does this get called automatically when it's destructor is called? Oh, unlocks. Yeah, there you go. Okay, it unlocks when it's destroyed. Yeah. So unique lock basically gives you defer lock. Where's defer lock? This is a lock guard. It's like the same thing as the unique lock. As an associated, unlock it. Okay. Oh, I see. So the lock guard is, if it's already locked, you can assume it's locked and create the lock guard. Oh, I see. Okay, and that'll unlock it afterwards. You could also just use unique locks and defer and then lock that way. I see. So what I was doing before with the lock guards didn't make any sense. It didn't make a lot of sense, I guess. Or was I using scope lock? I think I was using, no, I don't know what I was doing. What I was doing didn't make a lot of sense. Lock guard and scope lock are related to each other. So confusing. Lock guard. Attempts to take ownership. Okay. No, so I was fine, actually, the lock guard before. Alternative for lock guard that provides the ability to lock multiple mutexes. Oh, I see. Scope lock can be more than one. This could be more than one. That's what it is. Okay, this is so confusing. That's the difference between the scope lock and lock guard. Lock guard is just one. Yeah, okay, got it. That's, I think I've had enough. I think I've had enough. I don't want to read more. So the calling thread already has ownership of the mutex. Try to acquire. Do not acquire. Okay. So defer means you don't acquire. And then lock one, lock two, we'll lock the two of them. Adopt means it's already been locked. So, and this could be lock guard instead of unique lock. It's like the same thing. Basically the same thing. Apparently the same thing. What is unique lock anyway? So that was, what is unique lock again? What's the difference between unique lock and lock guard? All right, RAI style. Unique lock is not the same as, but it will when it goes, if owned, it will unlock it. Same thing, lock guard. Structs the lock guard. Yeah. Forget to give it a variable name. Default constructs a lock guard variable named mutex. Constructs a PR value object that is immediately destroyed, not actually constructing a lock that holds a mutex the rest of the scope. That's pretty funny. Whoops. I like that. Movable mutex ownership wrapper is unique lock, and what does lock guard do? Strictly scope-based mutex ownership wrapper. Oh, okay. So it's not the same. So lock guard versus unique lock. Oh, this is a movable mutex ownership wrapper, whereas this is scope-based mutex ownership wrapper. A little different. A little bit different. This one is not necessarily tied to this. Well, it kind of is tied to its scope. They're very similar. Are they both movable? I think one of them strictly scope based, the other one's not. So that's confusing. I don't know. I don't really know what the difference is, quite frankly. Don't they? Yeah, I mean, when it goes out of scope, they're both gonna. It's really annoying. I don't think it has any other member functions other than the constructor and the destructor. Yeah, that's kind of it. Doesn't really have. Is it lockable? It's a type of mutex, I think. It's a wrapper. Yeah. Whereas the unique lock is also a type of mutex, general purpose, has a few more member functions. I'm sorry, it's not a mutex. It takes a mutex as a template. Very confusing. I don't think it necessarily locks the mutex, so that's confusing. It doesn't lock the mutex. So this is deleted. It's not movable, I think. I guess is what that means. Effectively calls them. Okay. Ownership without attempting to lock it. It's undefined if the current thread does not hold a non-shared lock. Lock acquired by lock. Try locked. Oh goodness. Okay, so if it's not already locked, then it's undefined. Assumes that's already locked. Undefined if the current thread does not hold a non-shared lock. If it does not hold a non-shared lock, so sort of a unique lock, not a shared lock, but I don't know what that means to be shared or not shared. If it doesn't hold a shared lock, lock acquired by lock, try lock for, or try lock until on M. So the current thread doesn't have a lock on M, then this is undefined. Undefined if M is destroyed before the lock guard object is. Also undefined. Oh, that is so confusing. Oh my goodness. Which is different from the unique guard lock though. It's got a lot of other things going on. So it can do the same thing, 6, but yeah, okay, but it can do some other things too. All right, I think the unique lock is similar to lock guard. It just has more functionality. I think that's the basic understanding. The reason why I'm spending so much time looking at this is because I've been asked questions during interviews of things of this nature. They're just very specific questions that are like, why would you even know these things? Why would you even care? Let's see. In computing, a spurious wake-up occurs when a thread wakes up from waiting on a condition variable without the variable being satisfied. It is referred to as spurious because the thread has seemingly been awakened for no reason. However, they usually happen because in between the time when the condition variable is signaled and when the waiting thread finally ran, another thread ran and changed the condition, causing a race condition. If the thread wakes up second, it will lose this race and a spurious wake-up will occur. On many systems, especially multiprocessor systems, the problem of spurious wake-up is exacerbated because if there are several threads waiting on the condition variable when it's signaled, the system may decide to wake them all up, treating every signal to wake one thread as a broadcast to wake all of them, thus breaking any possibly expected one-to-one relationship between signals and wake-up. If there are 10 threads waiting, only one will win and the other 9 will experience spurious wake-up. To allow for implementation flexibility in dealing with error conditions and races inside the operating system, condition variables may also be allowed to return from a wait, even if not signaled, though it is not clear how many implementations actually do that. In the Solaris implementation of condition variables, a spurious wake-up may occur without the condition being assigned to the process's signal. The wait system calls call aborts and returns enter. The Linux pthread implementation of condition variables guarantees it will not do that, because spurious wake-up can happen whenever there's a race, and possibly even in the absence of a race or a signal. when a thread wakes on a condition variable, it should always check that the condition is sought is satisfied. If it is not, it should go back to sleeping on the condition variable, waiting for another opportunity. My body. Oh. Okay, I'd have to read that a few times to really understand what I read, but I think the basic idea is you could have a spurious wake up with a race condition, which is not good, especially given that these are supposed to be primitives to help you avoid race conditions. That's the whole point. Having all these synchronization primitives. Anyway, so okay, we already went over barrier. We used barrier. That was pretty cool. That was cool. I don't think we need to keep looking at scope locks and things of that nature, lock cards and scope locks. I think I have a better understanding now, though, of, or I'm starting to get a better understanding of unique pointers and shared pointers. Going over these unique locks and shared locks, it's very similar kind of a thing. All right, wait until main sends data. Unique lock m mutex wait cv.wait condition variable wait for this lock. So I need to look at that, right? What does cv wait do? Blocks the current thread until the condition variable is awakened. Okay, what's the condition variable? Has a wait with a predicate. Stop waiting. Atomically unlocks the lock. Wait causes the current thread to block until the condition variable is notified or a spurious wake up occurs, optionally looping until some predicate is satisfied. Bool stop waiting equals true. Atomically unlocks lock, blocks the current executing thread, and adds it to the list of threads waiting on this. The thread will be unblocked when notify all or notify one is executed. It may also be unblocked spuriously when unblocked, regardless of the reason. Lock is required. Wait exits. Okay, so we've got a lock, and we wait, and that means that we unlock the lock and block the current executing thread, and now we're waiting on this, whatever that means. I think this is the condition variable. So we unblocked when we notify. Okay, so it unlocks the lock, and now waits for this condition variable, which is like another kind of a lock. After the wait, we own the lock. So now we're waiting for the condition. We unblock. When unblocked, the lock is required. Okay. So we lock, unlock, and wait, and then when the condition holds, we relock and continue. So now we have the lock. Do some processing. Send data back to main. Process true. Worker thread signals data processing completed. Manual unlocking is done before notifying to avoid waking up the waiting thread, only to block again, so you notify for more details. And then there's also a loop, which is return ready. So ready is false. But when ready is true, then it'll wake up too. So there's another condition to wake up, but we don't necessarily need to have a condition to wake up. I think that's just to avoid a permanent deadlock type of a thing. So if the bool of stop waiting is true, which is this just returns ready. So when ready is true, it'll stop waiting. Somewhere in here, ready is true. Okay. So we start our worker thread. We have example data, send data to the worker thread. We lock LK, lock guard M. So we lock the mutex here, set ready to true. Signals data ready for processing. CV.notify1. Okay, so worker thread. We create this worker thread. Get this other lock. We wait on the lock. We have notify CV in that worker thread, and then now it continues, right? Unlocks and all of that, and notify one. So we notify one again. We're gonna come back to notify one, what that does. So this thread gets locked and then, or created, and there's a notification. wait for the worker join. So this is very confusing. I don't know what's going on here. Create this worker thread. This is another lock on M, the same mutex, right? So we acquire this lock and start waiting. And then we have another lock that tries to acquire, which this lost the lock. So now we reacquire the lock here, set ready to true. And the condition should be basically yes, that basically stops waiting after that. Signals data ready for processing. That's one way of doing it. The condition will be true here, which is not necessarily this condition that's true. It's just a condition variable, which gets a signal. And then it's going to go through and unlock and process and all of that. And it's going to notify one here, which I'm not sure what that does here, and same thing here. And then get the lock again. And then wait. Process should be true already. Oh, I see. So this is just waiting now. And then waits for this to finish. That's so confusing. So yeah, signals data, processing is complete, waiting here, and then back in main. I don't think this is really how it's supposed to be used. I don't think this is doing anything, the cv.notify1. Maybe I'm wrong, but I don't think this actually does what it's supposed to do. I don't know. Any threads are waiting on this, calling notify1 unblocks one of the waiting threads. Maybe I'm wrong, maybe I don't understand, but this one is waiting, this thread is waiting for this condition, or for a notification. There's this thread, and then this thread is, the main thread is waiting. There's nothing waiting here though, I don't know. It's so confusing. One of the waiting threads. Except notify one, notify all, and each of the 3 atomic parts take place in a single total order. Oh boy. This is so confusing. Sorry, maybe it's not that confusing. I'm just not that familiar with this. That's probably more accurate to say. Holy, this is so complicated. Sorry, it's not that. I don't know. It's just, I shouldn't say it's not that good. I don't know. I don't want to say that. That's maybe not fair. That may not be fair. Feels like it's pretty complicated. Maybe it is complicated. I don't know. So it just picks a random thread to notify. I guess that's fine. Oh boy. Excuse me. Oh, I'm getting tired. Maybe this will be the last question I do. I wanted to do more questions today, but this is probably enough. Condition variable CV, mutex CVM, I0, done is false, waits, need lock, standard mutex lock CVM, C out waiting, CV.wait, lock, return I is equal to 1, C out finished waiting, I is I, done true, signals, sleep, see out, notifying falsely, notify 1. Waiting thread is notified with I equals 0, cv.wait wakes up, checks I and goes back to waiting. Unique lock, mutex, cvm, is1, well done, not done, notify true change. Unlock, notify, thread, lock, waits, signals, join, waiting, notifying falsely, notifying true change, finished waiting. I see. So T1 waits is a thread, which gets a lock, CVM, mutex locks this lock, waits, cv.wait until I is 1, but also waits until it's notified as well. And then once it wakes up, it finishes waiting and done is true. And it'll reacquire, by the way, this lock, but it's a unique lock, so once it goes out of scope, it'll drop the lock as well. Okay, then T2 signals, so this one's executing, gets a lock and waits. This waits for a few moments, quite a few milliseconds, notifies falsely. Waiting thread is notified with I equals 0, cv.wait wakes up, checks I, and then goes back to waiting. So this other thread that's waiting, it should just wake up, right? What does the notify do? Unblocks one of the waiting threads, so it should wake up here and then continue. Yeah. 2 equivalent to while not stop waiting, wait lock. This overload may be used to ignore spurious awakenings while waiting for a specific condition to become true. Oh, excuse me. Okay, never mind. It's a little more complicated. Okay. Note that lock must be acquired before entering this method, and it is reacquired after wait lock exits, which means that lock can be used to guard access to stop waiting. Oh, okay. Excuse me. I don't know why I got so confused. I missed that. I didn't even read that before. I was wondering. I was like, this is weird. Okay, so it won't lock until this condition holds. All right, I got it. These functions fail to meet the post conditions lock.owns lock is true and lock.mutex is locked by the calling thread. Standard terminates called. Oh man, boom, whoa. For example, this could happen if relocking the mutex throws an exception. Dang, crash. Programming cannot continue. Just boom, terminate. Oh boy. Excuse me, I think I need to eat some food too. Abnormal program termination without cleaning up. Abort. Unless sig abort is being called by a signal handler past the standard signal that the handler does not return. Destructors of variables, automatic thread, local, and static storage durations are not called. Functions registered with @exit and @quickexit are also not called. Whether open resources such as files are closed is implementation defined. An implementation defined status is returned to the host environment that indicates unsuccessful execution. So abort, I think, is not great. Just program just gets destroyed. Not ideal. Normal termination with cleaning up. Abort is abnormal. Terminate is exception handling fails, which is program can't continue. Can be called directly. Implicit try catch is called. Calls the currently installed terminate handler. The default handler calls abort. Okay, so terminate will just result in abort anyway. I see, which is probably not good. Generally, okay, got it. And then exit's not the worst. It's a normal program termination with some cleanup steps. Turning from the main function. performs a normal function termination, executes exit. Cool. Passing the argument of the return statement or 0 as exit code. Cool. I don't know why I'm so interested in that. Quick exit. Not cleaning up. Okay, or add exit. Okay, there's a lot of things you could do here. I don't know why I find that so interesting. Okay. Anyway. Predicate which returns false. The waiting should be continued. Yeah. Okay, got it. So stop waiting does not throw. Same as 1, but it may also propagate exceptions by thrown by stop waiting. Okay, so I was wrong. So that wait is very significant, this part. Okay, so what I was saying before here was I was wrong. This notifying won't do anything basically to these. Won't do anything unless the condition is met. Maybe used to ignore spurious awakenings while waiting for a specific condition to become true. Note that the lock must be required before entering this method. It is reacquired after wait lock exits, which means that the lock can be used to guard access to stop waiting. That definitely makes things pretty confusing, but basically, excuse me, basically, it won't wake up. If you try to wake it up, try to notify it and the condition's not true, it won't wake up in that case. Oh, that is confusing. Okay. So this will try to, this is a false notification. Condition is not true, it doesn't wake up. Then say, well, I'm not done. IS1, notifying true change. Unlock the lock here. Notify, thread is notified. Oh yeah, I is set to 1 here, right? I is here. Now the condition is true. Now we notify it'll work. And then we can sleep and then lock the lock and keep going until done is true. This is basically just waiting. This locking is this lock is reacquired, so this basically will wait until this is finished, and then this unlocks. And then this unlocks too. It should only happen once. So it notifies falsely noticed. Okay, now I understand. All right, I was so confused before. I was so confused. I think this one was the one that really confused me. Yeah, because I don't know what the wait does. Right, okay. So it has to have to wait until return ready is true. Got it. So yeah, worker thread begins, acquires the lock, waits for ready to be true and to get notified. Then this example data, we try to lock, which we don't actually have the ability to get the lock because it's already locked here. It's M. Yeah, I don't think we actually get the lock there, right? It's already locked. Oh no, I'm sorry, this unlocks. Excuse me, this unlocks the lock first. So it's unlocked. So now it's locked. Set ready to true. Print. And now that ready is true, this can be activated. All right, still waiting. Then we unlock the lock, so it's still unlocked. This condition is true. And now we signal, and now this can pass through. And now we're waiting for the worker. So after the wait, we own the lock. So now the lock is relocked. Worker thread is processing. So we did this one. Now we do this one. Data after processing, which is example data plus after processing. Send data back to main. So now we say processed is true. So here we wait again, we get another lock, and then unlock here, but wait for process to be true, which is happening here. And then worker thread signals data processing completed. Get the next one. While this is waiting with the lock unlocked, this lock is unlocked here. So we lock, unlock, and then finally manually unlock before notifying to avoid waking up the waiting thread, only to block again. So you notify one for details. So notify one. So for some reason we manually unlock again. It should be unlocked here anyway, but maybe it's not unlocked yet, or something, I don't know. So we unlock and then notify, and then that'll cause this to break through. I don't know if you really need to, I don't think you, well maybe you do, I don't know. I'm not sure why you need to unlock here, but maybe you do. And this actually relocks at the end. It relocks here and then unlocks again for the unique lock. And finally back in main, and the data is sample data after processing, which prints, and then we join the worker. And the lock should be unlocked. Why would I need to unlock here? This lock. Oh, I think the lock is reacquired here. That's why you have to unlock. The lock is reacquired here, so you can't pick up the lock yet here until, yeah, I see. So you won't even, you're actually not even gonna lock here, you're gonna lock here. Not even gonna wait here, you're gonna lock here, and wait and lock there until this is unlocked. In which case then, this picks up this lock and unlocks and waits, and then you can notify. Could be a race condition here, I think. Maybe, I don't know. It's very confusing. There's a lot going on there. It's pretty complicated. Quite frankly, it's pretty involved. I think I get the idea though, but yeah, it's a lot. So in theory, you could use conditions. That's the whole point of this, is to try to use conditions for this same thing. Instead of I think a barrier is probably the simplest way to go, but condition might be first off, how do you create a condition? It's just, yeah, condition, you just create it, and then you also have the wait. Okay. So the conditions that I want to manipulate are foos and bars, right? And then maybe standard condition. It's a condition it's condition variable. And what I want to do is cv.wait. So first I get a lock on a mutex. Right, or M. And then I want to wait. I want to get a lock. And I want standard unique lock of M. So now we're going to lock, then unlock, and have a predicate. So we return foos not equal to bars. Okay. And what's going to happen is I lock M, then I unlock M and wait on the condition variable, and until this condition is true. And then what's going to happen is I'm going to print foo once the condition is true. So once the condition is true, which it should be, I think when they're equal, right? That's when I stop. Stop waiting is a certain condition. So when this is true, it'll stop waiting. So when they're equal, then I'll print foo, and I've got to notify when they're equal somewhere, somehow. And then it's going to lock, and then when this prints and the unique lock goes out of scope, it'll unlock. Automatically lock and unlock. Okay, and I've got something similar for the other side. Or similar on the other side. This, I guess, is like the correct way to handle what I was trying to do before. Almost the same code, just slightly different. The other condition is foo is not equal to bars. Now, what happens is after foo is printed, we increment the foos. After bar is printed, we increment the bars. Or I increment the bars. And let me see. Okay, a little over 3 hours. All right. Foos, bars, print foos, increment foos. Okay. After bars is incremented, then I can cv.notify 1. Yeah, cv.notify 1, and same thing over here, cv.notify 1. Okay, so these are both going to wait on these conditions. Grab a lock and wait. And first things first is, I think, notify and notify. So these are spurious wake-ups, potentially. So first thing to do is to notify, and so they both notify and they're both not waiting, so it doesn't do anything. Then they both are waiting, right, for these conditions. One should wait before the other and then notify the other, I think, something like that. That gets really confusing. I'm not sure. Maybe we could do the other way around. We can do foo prints and then waits. Maybe that's better. We'll do it that way. Something like this, right? Something like this. And on the other side, it's we wait before we print. So we're gonna print foo, increment foos, notify, and then lock, right? And wait. On the other side, we're going to, before we print bars, we're gonna wait, notify, lock. I don't know if I need to remove these notifications for now. Lock, wait. So this will lock, and then it's gonna unlock here, and then this is gonna lock and then unlock here as well. This should get a notification. So this should be locking or waiting before this occurs, right? This notification. Could have a race condition where this doesn't wait at the right time. It takes too long to wait, and then you don't get a notification. Yeah, it's a little awkward. Maybe these should both be locked. I'm actually not sure about this one. If they both lock, it'll make sure that if I both lock, then it'll make sure only one of them goes at a time. But the problem is that if this one goes first, then this could be, well, this will unlock the lock actually once it gets here, so that's fine. This will unlock the lock. And then this can get the lock. So if this one goes first, it'll unlock the lock and then wait, and this one will reacquire the lock, and then go through here and notify, and then relock or unlock and relock. This one, so that's if this one goes first. If this one goes first, yeah, this will pick up the lock and then unlock. This will pick up the lock, do these things, and then unlock. Where the notification should happen. So one problem would be, what if this notifies and basically you could skip this altogether if basically you only need to do this when foo is not equal to bars. Same thing over here. So this foo is not equal to bars. Yeah, that can happen too, where you don't actually need to wait at all. So what can happen is, let's say this one goes first. We notify the other thread. The other thread's not waiting anyway. Then this shouldn't wait either. Or no, the other one's not waiting. Then this should wait. This will start to wait. And the other one will be, it'll be unlocked. This will lock, and then we'll check if they're equal to each other. Right? If they're equal to each other, which they won't be here once we have a foo. So if they're not equal, this should just go. I think I did it wrong. If they're not equal, this should just go. Same thing. If they're equal here, then this should just go as well. We shouldn't even wait in that case, because the problem is that you have to wait for the notification, which, depending on the order you do things in, you may or may not see the notification at the right time, which is very awkward. That's what I'm trying to avoid here. So if you've already, so you print foos and you've already printed bars by the time you get here, there's no reason to wait. Because the problem you could have is that the notification that bars was finished may have already came before you actually waited, which is the problem. Yeah, that notification might get ignored. Yeah, I think that's the issue. So you basically do the same thing for both, right? Although I think one comes before the other. Yeah, something like this. Something along these lines. Let's see if this works. Not too sure. Oh, it can't be really implicitly captured? Oh, okay. Oh, what about this? This is a little bit more confusing, I have to say. I think I prefer the barrier solution to this. The barrier solution is a lot faster to program, a lot easier to understand, a lot faster to program. This is wrong too, top of it. Foo a bunch of times, and bar a bunch of times, okay. So if they're equal, so they should be not equal, then we need to wait for it to become equal, right? Should be not equal usually. It's not equal, then we wait. On the other side, if it is equal, then we want to wait until they're not equal. Okay, I don't know why I confused that. That was weird. This might just deadlock. I don't realize it. Oh, there we go. Okay. Perfect. So I think that's correct. I'm just going to go for it, see if that works. It's pretty, yeah, okay, there you go. So you can submit that a few times. So that's an example using a condition variable, which I kind of just learned what that even is. A little more complicated, a little more involved. There you go. 3 milliseconds is pretty good though. It's relatively fast. Not bad. Let's try again. So this would be like the correct way to do the condition that I was trying to do before. Definitely way more complicated though. Basically always unique lock, and then the idea is that you're going to print foo first, and then increment foos, and then notify the thread that's waiting. It should be the other thread that's waiting. And if they're not equal now, that means that you have printed foo, and you can continue here. This will reacquire the lock, then print bars, then notify, and then lose the lock, right? Now, when you notify on the other side, foos and bars should be not equal to each other because you printed foos now after this lock was no longer acquired, then this lock gets acquired, print foos should be not equal to bars, and then you should wait. But as I said, what can happen in theory is foos and bars are already equal to each other, in which case you don't wait, you just go straight in. It shouldn't really be possible, I think, for this to happen, but I think in theory it could. Like I said, due to a kind of a race condition, where the notification, like, you want to notify after foos has been processed, and you also want to make sure that like you're waiting, because you might just not be waiting in some cases when you notify, or it might be notifying too early. Is kind of the issue. So let's say we acquired this lock and foos and bars are equal. Now we need to wait, which then will drop this lock, and then this lock will pick it up. Now we print foos and notify, and they're not equal anymore. And so now this keeps going, keeps going, they're not equal, and this one, it checks if they're not equal. If this gets all the way through before this check occurs, then this gets skipped altogether. And the reason why that's important is because if this goes all the way through, let's say this just speeds up for some reason, it notifies at the end, this notification will get skipped. And that's why you want to skip this altogether and guard this in this way, because if you notify at the end, but you wait after you've been notified, in other words, if this completes in the time it takes to start waiting, then you're going to miss this notification and deadlock. That's the issue. Whereas if this gets all the way through, this if statement prevents this from deadlocking. Same thing on the other side. Same kind of idea. So yeah, that's confusing. It's really not obvious at all. But that was one of the issues I was trying to think through, like how do you logically avoid this deadlocking when one thread just so happens to process things faster than the other thread. That's, as I said, it's way more complicated than just using a barrier twice. It's keeping it really simple with a barrier. So that's another solution that could work. Again, I don't like the way he did it. I think you could technically get a race condition if one of the threads just happens to work faster than the other thread for whatever reason. Okay. but pretty interesting. Wait for, maybe. What is, maybe wait for is what I should use. Maybe I'm wrong about his implementation. He doesn't use the same one that I'm using. Although I don't know. I don't actually know. What wait for, what does that do? Standard recommends that a steady clock be used to measure the duration. So this is a little different. Yeah, this is this actually gives me a period of time and a predicate. So they used, no, so this is different. Yeah, the wait for, no. So I was right. This wait is the same as the wait that I have. It's just wait for, and C++ adds an extra timer on there. Each thread can wait on each other to set their corresponding foo printed and bar printed events. Each thread also resets the corresponding events with clear for the next loop iteration. Printed event. So you can use events too. 2 locks for the threads to signal to each other when the other should run. Bar lock starts in a lock state because we always want foo to print first. Oh, that's a good idea. Okay, yeah, I did that, but I didn't. I should have locked one initially. I didn't think to do that. That would have been a much better idea. Whoops. Okay, that's clever. I didn't realize you could do it that way. I used my own lock, basically hard coded a lock, which is not good. Shouldn't do it that way. I think this is the best way to do it. I'm glad I looked at the answers because I totally missed that one. Didn't even realize you could do it that way. Event. I should look at that. There's probably C++ concurrency events. Let's try that. Oh, I don't know if there are events. That's a good question. Yeah, concurrency support library. Event. No, there's no events. Okay. I think the best solution though, and the fastest and simplest solution is not the barrier solution, but I think it's the other one, the one that I basically went for initially. Fastest and simplest is just have 2 locks. Excuse me. M1, M2, and we just M1 dot lock, and these are going to be M1 dot lock here, and then M2 dot unlock. Excuse me, and the other side is same thing. Oh, hold on. And this is going to be the other way around, M2 dot lock and M1 dot unlock. So, let's see, start by locking M2, I think. Yeah, start by locking M2, and then after foo prints, M2 can then acquire the lock. Yeah, that's what you have to do. Okay. I don't know, for some reason I couldn't think that all the way through before. Just wasn't working in my mind. Just I couldn't see it. I don't know why. I was having a hard time. That's so much simpler than the other solutions. Even the barrier solution is a lot simpler. This is very clean. This is very good. Okay, I like this a lot. This is what I should have done the first time. Definitely would have been better if I did this first. Kind of disappointed in myself a little bit that I wasn't able to, why I hard coded a lock condition. I should be using the concurrency primitives to do that. So I guess that's the conditioned variable, I suppose. And the second thing is I should have been able to think that through, that all I needed to do was just lock M2 first to make sure bar doesn't go first. So M2 starts off locked, and then it gets unlocked by foo, and then it gets unlocked by bar. You know, then you pick up the lock by bar, but bar will sit and wait until foo finishes. Yeah, I mean, it's really simple now that I look at it, but it just didn't occur to me at the time. So yeah, kind of unfortunate, but very good to see the solutions. There's even more, I think. There's the events, which actually you don't have that in C++, I think, the events. So I guess we'll skip that one. Semaphores. I guess these are really just like binary semaphores or something. Really. Failed on my machine. Incorrect. Once threads reach the barrier, could have the foo thread process proceed to the next loop iteration. Yeah, it's incorrect. I showed that it's incorrect. A few people pointed that out. Cool. Cool. The semaphores, I think it's just the same as the locks, basically. This is perfect. This is the best solution. Just use 2 locks, 2 mutexes. This is a very good solution. It's my favorite. It's definitely a good one. Semaphore solutions. Yeah, I don't know about that. So the semaphore solution, I'm pretty sure, is just the same as the. It's just the same as the lock solution, but you just lock one of the semaphores first. It's like the same. The barriers, the semaphores, I think are good. The condition variable is a little more complicated. You can do it, but it's definitely not my favorite, I think. It's a little too complicated. This is a good question. This is like a really solid, like helping, like a good question to practice concurrency for sure. Yeah, I mean those basically are those binary semaphores are basically being used like mutexes pretty much. Atomic. Okay. Oh, it alternates. Oh, that's interesting. I didn't think about that. Make the Boolean atomic. Okay. Oh, that's why my condition was wrong before. I needed to make my Boolean atomic. So my code was just wrong before. My code was just wrong. It was not correct. It worked, but it was not correct. That's funny. Okay, good thing I looked at the solutions. So yeah, I should have made my variable atomic. Okay. Okay. Or maybe it was correct. I don't know. I'm not sure. Yeah, I probably should have used that, the atomic variable. I was gonna like quote unquote hard code the lock. And by hard code I mean write my own lock, write my own custom lock, write a custom condition. I should have used probably you made that atomic. I mean, it didn't really need to be. I guess it was okay. It was just a little bit awkward. Try one more. Okay. Semaphores as well. Alright, it's pretty good. It's pretty good. I think I had the fastest though. I did have the fastest. I'm surprised this isn't faster. This seems to go kind of slow. Seems like it shouldn't be this slow. Like I should have gotten 100% at some point, but yeah, I guess the other approach was faster. The one that used just used like a hard-coded while loop, hard-coded while loop with a boolean to check just a yeah, custom like gate, I guess we'll call it. instead of locking this first, which seems like it shouldn't be that much faster, but for some reason it's faster. Maybe this include is the problem. I didn't realize that's there. Like, that actually could be it too. I could be slowing it down. I don't know, maybe. Submitting it like 1,000 times. I'm curious about the runtime. That's really why I keep submitting it, to see. It has quite a lot of variation. I like this way though the best. This is definitely the best solution. It's very good. This is also very many hours of just looking at this question. All right, I should probably stop there. So let me stop there. So thank you for watching. I appreciate it. Hail victory, hail victory. And if you like this video, give it a like and subscribe for more. I think that's it for me today. I wanted to do more, but I definitely needed to spend some time like thinking about and reading and learning about concurrency. I think it's fine to spend like a few hours just doing that, because I basically haven't spent that much time looking at it or thinking about it. And yeah, well, today I did. Today I did. So I kind of understand it a little bit better now. Again, I prefer lockless concurrency as much as possible, but yeah, it is sometimes best to just figure out how to use locks and use it appropriately. And I definitely didn't do that like the best way, the way that I came up with. There were a few ways I came up with that weren't really that good. And then using some of the primitives and like thinking about it a little bit more clearly had better solutions. So anyway, yeah, so take care. Talk to you soon.